We've seen the construction of a confidence interval using the bootstrap, but of course, for many, many years, the bootstrap wasn't available. And how did it get done before that? Well, let's connect up the traditional formulas that you might see in old statistics texts, and current statistics texts, actually, for that matter, with the bootstrap. The basic idea of the bootstrap is that we have an original sample. It's the circle on the left here. And we'd like to know how unreliable or reliable it might be as a representation of the population that it came from. If we could, we would draw lots of additional samples from the population, but we don't have that population available to do that. Next best thing is to replicate our sample a huge number of times so that we have a hypothetical or a simulated population to draw samples from that represents as much as we know about the population that the sample came from, and then we draw lots of samples. Of course, we're not really creating new data here, but we are investigating the behavior of samples when drawn from a population that this sample might have come from. Now, in the actual practice of the bootstrap, we simply put the numbers back in the hat after we draw them so that we're sampling with replacement, and we skip that step of replicating the sample over many, many, many times. We could imagine yet another type of bootstrap it's actually called the parametric bootstrap, where instead of replicating the sample over many, many times, we pretend we got the sample from a normal distribution and we generate random numbers from that normal distribution. The normal distribution would be one that shares the mean and standard deviation of the sample, and then we would just draw lots of resamples from that normal distribution random number generator and observe the behavior of those samples. That's in today's computer world. Obviously, before the computer was available, the normal distribution could still be used, and mathematicians had figured out exactly how samples would be distributed when drawn from a normal distribution. And so researchers everywhere could use that reference distribution, that normal bell-shaped curve, to map the sample to figure out how it would be distributed, and then draw confidence intervals based on this familiar normal distribution curve. And it turns out that samples, even though the data are not normally distributed in the sample, many occasions the sample mean will in fact be quasi-normally distributed. And we have this mapping process where we standardize the results of the resampling. We subtract the mean from each resampled mean and divide by the standard deviation. And this allows us to compare any sample's resampling results to a single standard normal distribution. It's also called the standard error of the mean. Now, back in 1908, a statistician named William Gossett, who worked for a brewery, published this article in Biometrica, The Probable Error of a Mean. Published it under the name Student because the employer, the Guinness Brewery, would not allow its employees to publish research works under their own names. They did not want to publicize what methods they were using in the brewery. Gossett's goal was to find the sampling distribution of the mean. And if you look at his article, there's this quote. What did he do first? Well, he wrote down 3,000 values. It happened to be physical measurements from 3,000 criminals. The measurements were written out on 3,000 pieces of cardboard, which he shuffled, and then he drew them out at random in samples of 4, and then he calculated the mean of each sample of 4 and plotted it, standardizing it first, subtracting the mean and divided by the standard deviation. That's that jagged line you see in this figure. And then to that he fitted the student's t-distribution, which he had separately worked out theoretically. the formulas that are in the text are used to map a particular sample result to this t-distribution and build a confidence interval. There are actually a family of t-distributions. Depending on the size of the sample, you get a different t-curve. So here's the formula that you'll see for the confidence interval based on a t-statistic, where, let's go through these items actually one at a time. X bar is the sample mean. That little symbol there is alpha divided by 2. Alpha is the area that's left over from the confidence interval, so that if you have a 90% confidence interval, alpha would be 10%. And here we are looking just at one side of the interval, so this is the part that's going to be chopped off on the upper or the right side, and so we chop off alpha divided by 2. That's just a measure of how much we chop off. Okay, once we know our sample size, we know n minus 1, and we know alpha is what's left over after the confidence interval divided by 2. For a given sample size and a given alpha, there's going to be a single t value. It's going to be plugged in here, and then you sort of scale it up by multiplying it by the sample standard deviation and dividing by the square root of n to put it on the same units as the same scale, should we say, as the actual sample mean values if we could draw lots of them. So this expression taken as a whole is the upper limit of the confidence interval, and there's a similar one on the left-hand side for the lower limit.